Nature exploration is a video work dealing with the way in which technology is enabling man to explore his environment and explore areas of the environment which were previously unavailable to explore by other means, and also the ways in which he is adding detail to the areas that he's already explored. The Grand Canyon of the Colorado River is an appropriate place to begin a discussion of exploration because it was the last large area of the United States to be explored. And then only late in the 19th century did white men find out what truly lie between the Rocky Mountains and the desert expanses of the Great Basin. Native Americans, of course, knew all about the canyon for centuries. The Anasazi, the Havasupai, the Hopi, the Navajo all made their home in this area at various times and knew the canyon quite well, and some actually lived in the canyon. But they didn't have a written language, nor did they make maps, and it wasn't until the white man encroached on their culture that these things became a necessity. The first white men to view the canyon and to explore it in the contemporary sense to a very limited extent was an out party from Coronado's expedition in 1540, who enlisted the help of Indian guides who took them to the South Rim, where they saw the Grand Canyon for the first time. They produced a map even more simple than the one shown here, which was done in 1777. After that time, till the late 1860s, mountain men and two Catholic priests crossed the canyon but didn't really explore it. On July 6, 1869, John Wesley Powell left what's now Green River, Wyoming, with a group of 8 men and 4 boats with the intent of traveling down the river, making scientific observations and a map of the heretofore unexplored Colorado River gorge and basin. Powell's expedition provided Western civilization with their first reliable account of the fantastic natural wonder that lie in this large unexplored area of the United States. It captured the imagination of a large number of people after it was publicized, and numerous people journeyed to this area and made explorations, photographs, illustrations. Most of the exploratory teams carried with them a scientific illustrator at first, and later on photographers, all of whom tried to capture something of the essence of the area, some more accurately than others. These are from Dutton's Tertiary History of the Grand Canyon. And this is an early version of a topographic map, although seemingly very detailed, still filled with inaccuracies. From Powell's first journey, groups from the organization that he founded, the U.S. Geological Survey, periodically traveled through the canyon, mapping it in greater and greater detail with more sophisticated tools. This is a recent map of the Grand Canyon. It's really a triumph of cartography. It features thousands, literally thousands of miles of lines denoting the contours of this incredible geological area, also political and cultural boundaries, vegetation, roads, a very detailed map. However, it's two-dimensional. We now need better tools so that we can see things of this complexity in 3 dimensions as a volume. Remote sensing and image processing provides us with that tool. We can assign colors to a black and white image to denote altitudes. We can generate a perspective view of a landscape and move the sun through its path during the course of the day to see how it looks in the morning, and then later in the day in the afternoon. By being able to create a 3-dimensional model, we can view a terrain from any angle, and in so doing, inspect the effects of any proposed changes that we might have in that terrain. In other words, we can test non-destructively ideas which might have a huge impact on the environment. In this case, a dam on the Colorado River. In this age of complex problems needing quick and accurate solutions, we need to have tools, interactive tools of incredible sophistication that are equal to that task. Remote sensing of the environment and the visual processing of that information has already provided us with incredibly new and unexpected views of our environment. In order to illustrate the ways in which this new technology will be affecting us, I propose a trip around the world, with stops in various locations to demonstrate the ways in which this new technology will help us in our exploration and re-exploration of our environment.
We can go to areas that are already well known by man. One of the first areas that we're going to try here is the city of Vienna. The gray area in the center of the picture is the city of Vienna. The blue Danube River is the long diagonal line from left to right, or right to left. The red area on the side of the picture is dense vegetation. In most of the images that you're going to see in this video, vegetation is red instead of green because the images are sensed in a different part of the spectrum than our eyes are sensitive to. This is an area in Austria called Zell am See. It's a mountainous area, and you can in fact see a snow-covered mountain in the lower part of the picture. This is a summer image, and the vegetation is very strong, and that's why it is very intense red. If we were to look at it in the winter time, the area is mostly snow-covered. This is what happens if the satellite looks down in the winter time. We can look at different resolutions and see different levels of detail. This is the city of Paris, or a portion of the city of Paris. We're going to zoom in on this and look at it at a higher resolution. In this image, as we roam around it and look at important features, we're looking at data that has a resolution of about 10 meters. We can see objects on the ground that are 10 meters or larger. Things that are smaller than 10 meters are hard to see. This is a park in Paris called the Bois de Boulogne. We're going to go up to the northern part of that park. In fact, go down the Champs-Élysées. The square in the center of the picture here is where the Arc de Triomphe is. And this area is called the Place de la Concorde. The black area is the shadow of the Eiffel Tower. The Seine River passes diagonally through this portion and will in effect fly down over top of the Seine River, going through industrial areas and residential areas. You can see individual towns and buildings and alleys. You can see a soccer stadium, for example. Not only can we look at areas that are well known to man and well explored, we can look at areas that are less well known. This is Persia, the country now known as Iran. The Zagros Mountains are covered with snow and dense vegetation and toward the top of this picture. And at the very top, you can see the southern edge of the Caspian Sea. The city of Tehran is the gray area in the lower right. In this area, in this image, we've decided to try to make a map of the vegetation, to begin to do something to the data, to analyze it. The white areas in this picture have very strong, very large amounts of chlorophyll. The dark areas have very little chlorophyll. We can choose to color the areas that have a certain brightness or more, have a certain higher amount of chlorophyll or higher, and propose that these are areas that have a certain density of vegetation, forest cover. We can make a map of that instantaneously. We can go to areas that happen to be politically sensitive. The body of water that's diagonaling from the upper left to the lower right in this picture is called the Shatt al-Arab, and inside that box was the city of Abadan, where Iran and Iraq are presently fighting a major war. In the box now is where the Tigris and Euphrates rivers join to form the Shatt al-Arab that flows into the Persian Gulf in the lower right. The red area in the upper left of this picture where the box is pointing to now is a papyrus swamp. It's a swamp that is filled with papyrus reeds. It's the place where Thor Heyerdahl made his boat called the Ra, that he sailed down the Shatt al-Arab and tried to sail to Egypt. You can see along the river, the red areas, those are palm plantations. You can also see cultural features. You can see some black streaks here, which we'll get a little closer to and zoom in on, so you can see the streaks. You get very close, you notice that they're bright red on one end. These are oil flares burning off excess natural gas from Kuwaiti oil fields and Iraqi oil fields. You can see the flame at the tip. You can also see ancient historical things. This is an old path of the Shatt al-Arab as it flowed into the Persian Gulf some centuries ago, before it later changed its course to the present-day course. We're going to zoom in a little closer now into this area around the town of Abadan where the war is being fought right now, into the area that's shown in a box. The city of Abadan is in the lower middle right, and it's in the middle of that island. The war is largely being fought in the marshes in the upper left. We're going to use this image to show a little bit about how we make maps using images. We define certain areas on the map that represent certain land cover classes. For example, we're going to draw a polygon here, fairly carefully so we don't catch anything that we don't want. Draw a polygon around areas that are typical water. And then we're going to instruct the computer to look at the values, the colors inside this polygon, and summarize them and remember what they looked like, what those colors were like. We're going to do the same thing for 5 other classes. That first class was river water. We'll define a box here around what we'll call lake water, water that's either shallower or muddier and has a different color, more of a light blue rather than a dark blue. We're going to go up and define another area up here, this black fringe around the marsh, something we're not sure what it is, but as we get closer I think you'll see that it's a wet area near the shore, and it's probably a wet, very shallow marsh. Now we want to get a nice homogeneous area, so we'll actually go around areas that are the red areas that are pointing out into that body. You can pick any shape and define any volume, and then ask the computer to capture that area and summarize it in its memory. We're going to define an area around the red vegetation in the center of the picture. This area is palm plantation. The palms obviously grown very near the river where irrigation water can be brought up to water them. Date palms is one of the major export products of both Iran and Iraq in this area. Okay, we'll now look at some of the more barren ground areas. There are 2 areas that are visible. There's a whitish area here, which we're going to define. The whitish area is probably a salt pan, judging from its color, an area where water is evaporated and left salt or high quantities of salt on the surface. And then down in the lower left, we're going to define an area around this tannish substance. The tan substance is probably sand or surface rock. Now we're going to ask it to extrapolate this out to the entire image. And in that period of green and orange flashing, it did that. We can color the results and show what it's predicted is the representative colors there. You can see it does a pretty good job of extrapolating it. We can look at statistical analyses of the different colors and try to determine which ones are which and what are the statistical characteristics of them that allow us to be more or less accurate in classifying and making maps. This kind of analysis can be done in real time by an operator sitting at a terminal. This is the city of Baghdad in Iraq, the capital city of Iraq. The Tigris River meanders through this area. The city itself is the dark gray area along the river in the center part of the picture. In that area is the oldest part of the town, one of the oldest parts of the town. Traditional Arab architecture uses a courtyard. There's a large building built around the courtyard, and there are areas of shadow produced that end up, when you look at it from above, producing an area that's dark. This is because it's very hot in this area, and they want to preserve the cool, shaded areas when it gets hot. This area in the box now is an area of relatively modern construction, done in the last 20 years with the assistance of the Soviets. They don't use traditional architecture, and so the areas are very hot. It's interesting to be able to see architectural styles in an image taken from outer space. This is an area called Samarra, a town of Samarra. It's a very old town, a caravan town, a town along the caravan routes from the silk trade, the silk route. The Tigris River passes through and is dammed right at the town. The town is the gray area just below the dam. That image we saw before was the way the data comes down from the satellite without processing. This is after we've done a small enhancement, a global enhancement of the data. You can see that there's greater contrast, but still there's very little detail in the water. It's very dark. We do another enhancement, a local adaptive enhancement. We get greater detail both in the sandy areas and in the water areas. Now you can begin to see that the caravan routes used to set off in the compass point directions from the town over open space and created their own roads that radiate out over the dry desert area from the town. Now we go to the city of Riyadh, the capital of Saudi Arabia. Riyadh is a relatively new city, a city that uses a great deal of asphalt, a city whose construction ends up producing a darker surface than the surrounding land. We can do complex statistical analysis on this data. This, for example, is something known as a principal components analysis. And what it allows us to do is it allows us to see the different soil types and different surface types in clear colors. You can see that there is a great trend of geology from the upper left to the lower right, areas of homogeneous color, blue and green and yellow and red areas that are streaking from upper left to lower right. A man who wants to make a map of the geology of Riyadh can use this as an indication of where the different rock types are without ever visiting Riyadh. We'll move on now to the area of China, areas that are very exotic and remote. First place we'll go to is the city of Chengdu in China, interior China. It's a city not well known in the West, but a city of 5 or 6 million people. It's a city that has a lot of air pollution problems and is located in the middle of a great agricultural basin. In the image here we can see the air pollution. We can see the clouds, mist, the haze over top of the city. You can quantify where the sources of it are if you know that the winds come from the lower right, from the southeast. You can tell that then the plants are to the east of the city and they're blowing the air pollution over the city. Now we're going to an area of lowland central China, an area of active rice cultivation. The red areas are areas of strong rice cultivation. The gray areas are areas of either recently plowed and harvested or recently flooded rice paddies. First thing we're going to do is attempt to produce a pure texture image of this, to see only the edges of the colors, the edges of the paddies, the edges of the streams and rivers, and remove as much as possible the variations in color. We can do this to enhance edges, but we can also do the opposite, try to remove the edges and enhance just the color. This ends up producing an image that looks something like an impressionist painting, pure color. This is an area in the wintertime as opposed to the summertime. The black spots, particularly in the upper right of this picture, are villages in China. And maybe we want to do a little analysis of the distribution of small villages in China. How much are they separated? How big are they? And how do they interrelate? We can define an area in the upper right corner, and we can select out areas that are small and dark and color them red. And then we can filter these areas to remove long, thin areas that might be roads or canals, so that we produce only the things that are lumpy. There they are. Those areas are villages in China, and you can see the distribution of them, that they're spotty. And we can overlay them in orange over top of the original scene. An urban planner can tell something about the transportation requirements by knowing the separation of the cities. We can go to the area around the capital city of China. In the lower left of this picture is a small box, which is very hard to see, gray area. That's the city of Beijing, or Peking, China, the capital of China. The mountains to the north are covered with vegetation, and that's why they're bright red, and there are a couple of large reservoirs up there. We're going to zoom into the gold box in the lower left now and look at Beijing in higher detail. Now you can very clearly see the box that is Peking. But you can see it's also not a real box, it's a parallelogram. That's a distortion caused by the satellite scanning the Earth as the Earth is rotating underneath it and getting, therefore, a skewing of the image. We can ask the system to correct that, to put the image into a map projection, in this case a universal transverse Mercator map projection. Now we can see the city of Beijing is a big square with a very small square in the center, which is the Forbidden City, the home of the emperor, with a white area at the bottom of that inner square, which is Tiananmen Square, where Mao is buried. We can see the Summer Palace is the large lake in the upper left next to the mountains that are bright red. We can see the urban areas as gray areas and the agricultural areas around the urban areas. We can make a map of different residential densities, red being high density, brown being medium density, yellow being low density, greens and blues, vegetation and water. By knowing the population densities of each of these residential densities, we can predict the overall population of Beijing and be accurate to 5% without ever visiting Beijing. In some cases, the census, the Chinese census, is only accurate to about 5%, and we can be accurate by looking merely at a picture from outer space. Now we're going to go into some of the more exotic areas of the southern China Sea, to Borneo and Bali. First to Borneo. This is the coast of Borneo where a large river is entering the South China Sea. You can see the water in the upper right and the vegetation in the lower left. You can see puffy cumulus clouds that look like little blobs of cotton. You can see that this is an area which is very much dissected by channels of water which are shown dark. This is a mangrove swamp. This is an opportunity to show what the satellite sees. It actually looks in 4 spectral windows. It looks at the light in the green and red and 2 infrared portions of the spectrum and gets different numbers for each one of those spectral windows, which it can use for classification purposes. You can see that the world looks different in these different spectral windows. In the upper left, which is the green part, water is bright and land is dark. But in the lower left, which is an infrared image, water is dark and land is bright. That's because vegetation and water have different reflectances in different parts of the spectrum. We can look at areas that are absolutely impenetrable jungle. This is a rainforest in Borneo with cumulus clouds over top of it. It's almost featureless. There's just a river showing and a little bit of bright red and dark red, but it's almost featureless otherwise. And that's because it's a very homogeneous forest, a great mix of different species uniformly mixed to produce almost a texture. In some cases, some of the disadvantages of using a satellite are the noise that it introduces into the data. We're going to look at this a little more closely. On the left side of the picture, we have the data as it's originally sensed by the satellite, and it has a horizontal striping pattern. I think we'll get a little closer here so that you can see it more clearly. The right side of the picture, we've removed that striping using a computer technique so that you can begin to see the actual texture of the surface beneath, how the vegetation has some texture which is somewhat obscured by the striping that you see on the left side. We've gone now to the island of Bali, and we're going to do an enhancement while you watch. We've looked at the raw image, which is very dark and a very low contrast. And what we're doing here is we're going to enhance the individual colors individually. First, we're going to work on the red part of the spectrum. In the lower part of this plot is a histogram of the brightness values of the input data, the data as we receive it raw from the satellite. In the upper part of this window is an expanded histogram of the brightness values after we've done an enhancement. And we're drawing a transformation, a mathematical transformation of the data with the yellow line. The idea is to stretch those histograms out so that they fill the whole horizontal space. First we've done the red, now we will do the green. It's an interactive process, and as you do it, you see the results on the screen behind the plot. Getting the green a little too bright. Now we turn down the brightness of that just a little bit. And now we have red and green more properly balanced. Now we're going to go on to the blue part of the spectrum. The blue has a very narrow distribution. Its brightness ranges are not very well spread. And we're going to have to spread them out by drawing a set of lines that instruct the system to spread out that distribution and give us a greater contrast in blue. And now you can see in the background that the image has a lot more brightness and contrast than it had before. You can see that there are 2 great mountains in this picture. There's one mountain to the right side and another mountain to the left side. And that these mountains are great volcanoes with great lava flows. We're going to go now to Australia. We're going to start to look a little bit more, as we're in Australia, at the water. In this area, in the area of Brisbane in Australia, this is the town located in the central bottom of the picture on the river. We're going to enhance not the land, but the water. We're going to try to get greater contrast into the blue area there. You can see now that we can see various slight changes in the brightness of the water that are caused by either the fresh water of the river carrying mud down into the ocean, as this is an outplume from the river, or various shallow areas, areas where we can see the bottom. In fact, in the center of this box, there is a diagonal line going from roughly 11 o'clock to 5 o'clock in the center of the box, which may be the trail of a ship or a submarine as it passes through the water. It's a long, straight line, and normally currents don't flow in such straight lines, so this is a man-made feature. We can also look at some of the islands on the right side of the picture, and you can see this island has a ring around it. This island probably has a coral reef just offshore. We can go to an area around Adelaide in Australia and begin to look at the world through very different eyes. This is the way the world would look if you were looking through the eyes of a person, where vegetation is green, where dry hills are brown, and where salt evaporation pans in the upper left actually are kind of a rusty red. This is what the eye would see if you were in a satellite as an astronaut. This is what the satellite sees, because the satellite uses infrared portions of the spectrum. This is what the satellite would see if it used thermal parts of the spectrum and saw temperature as opposed to brightness. And this is what it would see if it looked at a transformation of the different brightness values. There are many different ways of looking at the Earth. And one of the important points is the new technology gives us new eyes to see things. For example, we can see beneath the ocean. This is the Abrolhos Islands off the eastern coast, the western coast of Australia. There are a series of islands with coral reefs, and perhaps we want to navigate a ship through this area. We want to produce a sense of how deep the water is. We can look at a negative of the image and get a feeling for where the shallow area is by where there's color, or we can make a contour map, blue contours being relatively deep water, red contours medium depth, and yellow contours very shallow water. You could navigate a boat relatively accurately using that kind of an image without ever visiting. We can look in very different parts of the spectrum. Here we are in southern Africa. The first place we're going to look at is in Zambia. We're going to look at some data where we are seeing in minute variations in the Earth's gravitational field. This is a contour map of that data, where there are areas where the gravitational field is slightly weaker or slightly stronger. We can look at this in a grayscale, which means that dark areas are weaker gravitational field and light areas are a stronger gravitational field. And you can begin to see that there are areas that have meaning. There are structures, there are shapes, there are things that are apparent. Different ore bodies beneath the surface have different densities and therefore slightly affect the strength of the Earth's gravitational field. We can not only look at it in color, we can look at it in 3 dimensions in color and begin to see this ridge shape trending away from us in this image. That may be some rift, some shallow point in the Earth's crust that is varying the Earth's gravitational field. We can go into the whole country of South Africa and look at it with gravitational eyes and see different structures that are apparent in this variation of the Earth's gravitational field. There's a U-shaped structure, which we're going to highlight with a box. This is an area that's very interesting from a geologic point of view. A lot of the world's gold and diamonds are produced there. And it would make you, looking at this image, want to explore other structures that are like this, as over in the central left, another U-shaped structure. Perhaps there are interesting pieces of geology there. We can go into another area, in this case into another portion of Africa where we're looking in magnetic eyes. We're seeing variations in the Earth's magnetic field as opposed to gravitational field. And we can see 2 different kinds of structures here, horizontal lines and angled lines. We also see dots, as are outlined in red here. That's one of the most productive copper mines in the world right there. And neighboring it is another area which is just being opened up for copper mining. You want to ask yourself, though, what is this area, for example, or this area? By using these magnetic eyes, you can see things that are not visible in a normal image of the surface, and perhaps discover new deposits of copper because they change the way the Earth's magnetic field is propagated in that area. We can look at concentrations of different minerals in the soils. We're seeing a series of elements shown in the left, and their concentrations in this area in the soils. There's a great deal of pattern here. And the soils are made up of the subsurface rocks. So in this case we see iron and cobalt and silicon, or barium and iron and niobium. You can see a great deal of pattern here, which may direct your mining techniques, because you may want to find areas that have higher mineral content by looking at the constituents of the soils that are made from the rocks below. We go to another way of looking at the world, in this case a three-dimensional way of looking at the world, where we can actually see beneath the surface. In this image, we're going to be looking at the surface of the Earth as a three-dimensional cube. This is an acoustic image, a seismic image, and we're using it to explore for oil. By making a loud thump on the surface and listening for reflections below, we can figure out where the layers beneath the surface are, where the strong reflectors and the weak reflectors are. We can move up and down in this volume and see what kind of structures are beneath the surface of the Earth without actually going down there. And you can see there's some dome-shaped structures that are shown here, almost like tree grains, with lines that are faults passing through. This is an area that would be very interesting for producing oil. In an image like this, which is another three-dimensional image, we've actually tried to color the oil green. And you can see in this image that where there's a well shown as number 3, one of the biggest commercial applications of the modern technology at the present time is in prediction of weather. This is Hurricane Allen as it passes Cuba a few years ago. You can see the eye of the hurricane, and you can see the hurricane as it turns in hour intervals as it's passing southern tip of Cuba. You'll learn a lot about the structure of this hurricane, but you may want to again see it in 3 dimensions and get a feeling for what its shape is. That can be done fairly easily. In this area, we've suspended a map of the latitude and longitude grid points over top of a 3-dimensional image of Hurricane Allen. You can see the eye of the hurricane in the center of the image, and you can see the swirling pattern around it. Or we can actually take a little hypothetical spaceship ride in toward the eye of the hurricane and back out. You can see the shapes of the clouds and where the clouds are highest and where the clouds are the thinnest. Our trip around the world is almost over now. We've returned to the west coast of the United States, where we're going to do a little more examination in detail. We're going to look at another weather image that sees temperature. We're going to draw a line across the surface of the ocean and plot the temperature profiles. And you can see as you go from north to south, the temperature rises as you would expect. The water would get warmer. In the green, which is the visible part of the spectrum, the rise is much harder to see. And in the blue, which is the ultraviolet part of the spectrum, the atmosphere is opaque and you can't see the surface at all. The atmosphere looks much like the atmosphere of Venus. We can look at radar images. This is an area around Santa Barbara in California. And we can see the land on the right side of the picture and the ocean on the left side of the picture in radar. In this image, bright areas are strong radio reflectors and dark areas are weak radio reflectors. The satellite in this case is carrying its own radar beacon that it blasts out and listens for the reflections that come back. It's an active sensor. This is a reservoir in the mountains south of Santa Barbara. Now we come out to the coast and you can see the difference in reflectance between the water and the land. And as we move down the coast, you can see how we've gone from natural mountains now into agricultural areas, and you can see the different textures of the fields as they reflect different amounts of radio waves. This is the town of Oxnard going past, where you can see the small buildings are a jumble of radio reflectors. We can go out into the water and see some very strong reflectors. These little pinpoints of light are in fact offshore drilling platforms, which are very strong reflectors of radio waves. You can also see natural currents, variations in the height and texture of waves. And you can see a couple of great black smears. These are caused by oil seeps. The oil is rising to the surface and dampening the wave action on the water. We can show you some of the high detail and low detail images that are being postulated in the next few years. This is what the satellites have been seeing for the last 10 years. data which has a resolution of 80 meters. You can see that the world looks very coarse and blocky in this resolution. It's hard to see features. Today, we are now beginning to see data that is at 30-meter resolution, which has this kind of quality. And in the next 2 years, we'll see resolutions of 20 meters and 10 meters. We're beginning to see individual roads and individual houses and buildings. If we look at it in a split screen so we can see all 4 resolutions at the same time, you can see at the lower right, the 80-meter data, and the upper left, the 10-meter data, that there's a much greater amount of information, where the 80-meter data has difficulty determining just areas of blue and areas of brown. The 10-meter data can show you individual houses and edges of fields. Go into the San Francisco area. This is a San Francisco image taken in the early summer where the vegetation is very strong, and that's why the land is very bright red. You can see San Francisco is at the end of the peninsula that's rising up like a great thumb. The fog and the delta area around Sacramento. We'll go into that yellow box. Now we're in the late summer and the vegetation is weakened some. We're also at a higher resolution. You can see fresh water from the low tide passing out through the Golden Gate and then spreading out in a fan shape into the cooler, clearer ocean water. We can zoom into the area around Palo Alto. The city of Palo Alto is the gray area in the center, slightly to the left of the center of this picture. We're going to zoom in on the stadium. This is where the 1985 Super Bowl was played. This is an image of the Stanford Stadium on Stanford University campus. Now we're looking at data where the resolution of the pixels is measured in 1 meter, 1.7 meters to be exact. And we can see the individual stands and even see the individual lines on the football field. You can see baseball fields and pitchers' mounds. You can see individual cars running on the roads, individual apartments and walkways, paths. This kind of data is only just now becoming available from airborne scanners, from scanning aerial photographs, conventional aerial photographs. This is the quadrangle of Stanford University, and we can drive out along University Avenue toward the city of Palo Alto. The future holds even higher resolutions measured in centimeters and meters, with much greater numbers of spectral bands. The amount of data we'll be able to see is increasing astronomically. To end this video, we're going to look at the area around the Yosemite National Park. This is the Landsat scene, what Yosemite Park looks like in this image. The Yosemite Park that we know is in the lower portion of the picture, and the Grand Canyon of the Tuolumne is in the upper part. This is topographic elevation. Dark pixels are low, light pixels are high elevations. We can look at this image in a shaded relief map and get a feeling for where the low areas and high areas are by putting the sun in a particular place and shading the surface without considering its color. We can look at high slope areas, which are colored white here, and low slope, flat areas, which are colored black. Get a feeling for where the steep areas are. We can look at biomass. Light areas here have a large amount of chlorophyll. They're very highly vegetated. Dark areas are less vegetated. We can look at land cover produced from maps that are already known of the area and see where the streams are and where the roads are and where the different vegetation types are. We can combine this information and produce analyses. This is an analysis that tries to find the habitat of a marmot that likes steep slopes, an afternoon sun. To end this sequence, we're going to take you on a hypothetical helicopter trip down through the Yosemite Valley. But this is a way of allowing us to visit not only Yosemite Valley, but visit the surface of Mars if we have the proper data, and fly around it, and know what it's like to explore it. The future of these techniques of digital processing is unlimited. We're getting higher and higher resolution data. We're getting stronger and more powerful processors that can handle this data. The questions we're asking are more and more complicated, but we're able to produce a more and more analytical response. We don't have to guess now as to what the change in view would be like if we filled an area with water. We can actually simulate the view and see it and quantify it. The future of exploration is not going to be the same anymore. It may need to be done by ground truth, but it will be assisted by using techniques that an armchair explorer can do. And he'll have a great deal of power. This person will be able to see what he wants to see, simulate what he wants to simulate, and hopefully produce a better world for us all.